regarding ongoing.
So good morning, everybody. Welcome to the 12th edition of the Code of the Month. Today we have the pleasure to have to host the COE MaX Materials as Exascale, which is dealing with codes, a lot of codes for computational materials science. So we will see a short introduction into MaX given by Daniele Versano, and then the main talk will be given by Pablo Ordejón of the Catalan Institute of Nanoscience and Nanotechnology, ECN2 for short. So I'm pretty sure we will have a very interesting introduction into computational material science, which field with great promise. So the floor is then yours, Daniele.
Okay, thank you very much, Guntram. So let me present myself. I'm Daniele Versano from the Institute of Nanoscience, CNR in Modena. And I will give now a very flash presentation of the Center of Excellence in MaX, and then I will leave the stage to Pablo for the Code of the Month. In particular, in the MaX Center of Excellence, I do coordinate the training effort. So just to give the context of where the MaX Center of Excellence operates is in the exascale challenge in high-performance computing. Here, just I listed a few of the most powerful machines on the right of EuroHPC that we have in Europe that are now reaching the exaflops, and similar efforts are in the US or also in Switzerland. And this is an abrupt technology change, and action is needed for the full exploitations of softwares in these heterogeneous machines. So these exascale challenges is also an exascale opportunity, and for what concerns MaX, MaX it is based on softwares that do calculation based on quantum mechanics, atomistic modelings to simulate properties of materials and eventual interfacing with multi-scale approach. And so we are talking about electronic structures, highly accurate calculations, and the opportunities both in terms of accuracy of the results we can get thanks to this exascale machine, suit the opportunity through high throughput screening and possibility to have improved modeling in terms of complexity. Just to give a couple examples, this is a simulation on a very large system. This is a graphene sheet on top of an iridium surface with a cobalt layer. And we are now able to simulate with high precision the outcome and provide interpretation to photoemission experiments. And this is possible only thanks to the high performance computing. And just to provide another example, this is an example on high throughput screening of different materials. On the left, it is in high throughputs on colors of metal alloys. On the right, it is it works on computational screening on exfoliable materials to individuate new two-dimensional materials. So at the core of MaX, there are 5 codes: Quantum Espresso, SIESTA, that is the code of today, Yambo, Big Tifty, and Floor. And these codes are at the center of MaX since its first phase. Now we are arrived to the third phase. And MaX is based in Modena, Italy, with 17 European partners. All these codes are focused on electronic structures, but they are complementary in each other's in terms of basis set or in terms of features of quantities they can do calculate with accuracy. So here on the left again, these are the codes plus AIDA, that is a platform for high throughput calculation for orchestrations of codes. And here just to point out that materials and chemical science, they occupy a large part of the software that are currently used in EuroHPC machine. This picture is probably a bit old, but I mean, I don't think it changed much in the last year, the picture. So they are widely used open source or all open source community codes. And here just some selected activity on MaX. It's focused on the parallel optimizations, performance optimization, and porting of the codes on hybrid architecture, in designing of exascale workflow for selected scientific challengers, co-design, hardware software co-design. There is also focus on energy efficiency, and last but not least, a large effort on education and training. I will come back to this in my last slide. These are the partners. So at the core, there are the codes. We have academic institutions that are experts in electronic structures simulations, together with HPC experts and data centers. So many of the data centers in Europe, and as well as technological design partners. Here, just to point out that these codes are widely used all over the world. They collect around 4,000 citations by years, so they're widely used in university and also in companies. And here it is a pictures of the peer-reviewed publication citing MaX code, and we can see the distribution that's mostly all over the world, Europe, US, China, India in particular. This table here is the deployment of the codes in EuroHPC systems. The dark the green is the fully deployed machines, the codes on the different machines. In some cases, they are demonstrated, are supported architecture, a work in progress, which is that the picture is quite green, and we are still working to complete and to have a full deployment of all the codes on the EuroHPC machines. Besides EuroHPC machines, they have been also ported in ARM architecture as Fujitsu, for instance. Beside the porting optimizations, we are developing a workflow on selected challenges as electronic and heat transports by first principle, design and control of nanomagnetic system, and complex catalytic photovoltaic reactions, and also a focus on biological and biomimetic materials. So we are working on designing and developing exascale workflows to approach these big challenges. So I'm going to conclude just to point out our efforts with on training and education. We used to organize schools and hands-ons with theoretical foundations and best practice, hands-on with best practice and in HPC environment. And this is just a list of this year, of the events organized this year. So we cover all the MaX codes. And this is the distribution of the attendees. We trained nearly 600 people from all over the world. All the materials we develop and we prepare for the hands-on is collected, and it is uploaded in a new platform we are developing with other entities, where the video lecture, as well as training materials and exercise and so on, they are freely available, and highly curated video lectures that are that people can then be followed at his own pace. So with this, I conclude my very short presentations, and I hope you will enjoy the talk by Pablo Ordejón on the SIESTA code. Thank you very much for your attention.
Okay, so can you see my screen?
Yes, full screen.
Yes, all right. Okay, so good morning. I'm Pablo Ordejón. I work in the ICN2, which is the Catalan Institute of Nanoscience and Nanotechnology in Barcelona. I'm one of the members of the MaX project since the beginning of MaX, and I'm going to talk about one of the flagship codes of MaX that Daniele explained in his introduction, which is called SIESTA. So SIESTA is a density functional theory code for large-scale computational material science, and currently we are moving and we are working to make it even more efficient in high-performance computing environments. So I will give you a relatively long introduction to why material science and material modeling is important, and then introduce very briefly DFT, and then go on more on the technicalities of the SIESTA code. So I will give a relatively long introduction for the people who are not really experts in material simulation, which I guess are many in this audience. In preparing this talk, I have the pleasure to have the help of several people who are strongly involved in the SIESTA development, and in particular, Alberto Garcia from the ICMAP, which is the Material Science Institute here in Barcelona, very close to my institute. Alberto is the main developer of SIESTA since several years ago, many years ago, and he's really the one making the most of the contributions to the development and the maintenance of the code. And then 3 postdocs in my group, Federico Pedron, who is also lately very much involved in the development and maintenance of SIESTA. Then Nils Wittemeyer, also in my group, and Hernán de Freitas Martins. They are 2 postdocs working on specific aspects of the SIESTA development. So let me go to first introduce why materials are important. Part of this slide was already shown by Daniele. The materials are tightly linked to the progress of humanity, even to the point that the ages are usually named with the materials that were developed in that age. So the Stone Age, the Iron Age, now the Silicon Age. So materials are everywhere. They are at the core of our technological progress. Sometimes we forget that, but just think about the current issues of energy generation and storage, which is a huge problem for mankind right now. The main progresses that are being made in new energy sources and energy storage devices are due to new materials, to development of materials which are more efficient, are easier to fabricate, are more clean, etc. So all these progresses depend on finding new materials and designing new materials. Catalysis is another very clear example of that. So there is a lot of research in materials, and most of this research is somehow linked to a human need, to a societal challenge. So if you look at the issues of interest, for instance, in a journal like Nature Materials, you will find many issues which are directly linked to technological applications, which are important to help us overcome problems that mankind has right now. And materials modeling is rising to the level of being able to help very much and to boost the process of materials discovery and development. So having access to several things that have happened simultaneously is allowing us to really use modeling as a predictive tool to help in the development of materials. And these are a few things that are happening or have happened that are helping in this direction. So modeling in the sense of methods for modeling, mathematical models, and so on, they have been progressing very much in the last 20-30 years, but also the codes that implement these modeling tools and these methods. And of course, the HPC infrastructures, we are now moving to the exascale era, and that's allowing us to do heavier and much more CPU-intensive calculations. But also lately, the data storage, data management platforms are providing a wide avenue for materials discovery, very much linked to artificial intelligence. So all these things together and putting materials modeling and simulation in a place where they can be already quite predictive and complementing or helping the development of materials. This is just a slide that I took from Nicola Marsari that already has a few years ago old, that is telling that simulation techniques are really becoming a powerful technology with all these combination of things that may in the future be a multi-trillion-dollar technology that will be developed in the next few years. So we got to the point that this kind of cartoon is actually becoming a reality. So many years ago, theory and simulation, or computer simulation was used kind of as a guideline, but not very much to be trusted. Experiment was the one to be trusted. But currently, simulation is being the guide for experiment more and more. And that's because the simulation techniques have really improved very much. And they are now in the position where they are really predicted. They can, without resorting to experimental information or resorting to very small amounts of experimental information, to be able to predict the properties of materials and to design new materials for specific properties and applications. And that part of that, a big part of that, has come from what we call the first principles paradigm, or the ab initio way of doing things, which is to start from the modeling of materials from the very basic equations of physics, which in particular is quantum mechanics, because materials are made of atoms and electrons, and these are quantum particles. So if you start your calculations with the basis of quantum mechanics, then you have a predictive power, because you are not assuming any specific a priori knowledge of your system, but you are solving things as nature does from very first principles. That's only the first step in the actual and powerful simulation of materials, which we have right now, which is more in the multi-scale idea. But you have to start with the basic principles to build models which are able to reproduce larger scales or longer times. You have to start with something which is based on first principles and from quantum mechanics. And that's what we call electronic structure methods are currently doing. They are solving the quantum mechanical equations in a much more efficient way than before. They have become very, very accurate, highly accurate and predictive, but of course they are very computationally demanding. They need a lot of CPU time and very high powerful computers, and that's what we are starting to have right now. So quantum mechanics and materials modeling is really a case for high performance computing. So let me tell you what are the basic equations and the basic ideas that we built upon. So in this kind of methodologies, quantum mechanics, what we solve is the quantum mechanics equations for the electrons. So in particular, the Schrödinger equation, which is this differential equation. You have here the double derivative with respect to position, and then you have a potential here that applies to the electrons. So these are equations which are complicated. These are continuous differential equations, and actually they are coupled, because I'm plotting here the equation for just one electron, but this electron is coupled to all the others, because in principle this wave function is a many body function that depends on the coordinates of all the electrons. In the theory that we'll talk about later, which is density functional theory, you simplify the problem by writing a Schrödinger equation for a single electron, but that's coupled to all the other electrons by means of the potential. So the potential couples one electron to the others. So you have to solve many of these equations, one for each electron, but coupling the electron with all the other ones. Okay, so this is the bottleneck of this kind of calculation, solving an equation like this for each of the electrons of the system. If you have many electrons, that's a very heavy calculation. Then the atoms, the nuclei, typically they could also be solved in this way with Schrödinger equation, but nuclei behave typically as classical particles, so you just solve Newton's equation of motion. So for each individual position of the nuclei in your system, you solve the Schrödinger equation for the electrons, and from that you compute the forces and then see how the atoms move. So with this procedure, you can simulate the response of the material to any external property or any external stimulus like temperature, pressure, radiation, etc. So with this scheme, going from the very first principle basic equations of how the electrons are moving to the atomic motions, you can simulate the behavior of materials under different conditions. And that's what we do in this field. So with that, you don't only get information about the electrons, so the electron charge density or the electrostatic potential around the atoms or the band structures of the electrons in the system, but you also get access to structural properties of the material, like phase diagrams. So for instance, energy versus volume for different phases of the same material, and trying to see which phase is the most stable, when there is a transition between that phase and a different phase, and so on. Structural properties of the material. You can also look at chemical reactions, how the atoms change in position when a reaction takes place, vibrations of the atoms, any kind of property that depends on what the atoms and the electrons are doing, essentially. And as Daniele was saying, this high-performance computing evolution is allowing us to go into different improvements of our calculations. One is complexity. With big computers, we can solve bigger systems, and we can solve systems which are starting to be to have the complexity which is necessary to tackle technological problems like batteries or solar cells, like I mentioned before. But there is also the possibility of accelerating the materials discovery through high throughput screening, making very short calculations and very quick calculations, but very many of them in tens of thousands of materials to select materials which have the properties that we need for specific application, and select them using different criteria of for instance, what is the aqueous stability of the lattice site, or so. And the other thing that high-performance computing and the exascale coming to place is providing is that we can make calculations which are more accurate. Of course, the more accurate the calculation, the more expensive it is. So if we have large machines, then we can compute properties which are much more accurate, or compute properties which are much more complicated to compute. So for instance, one of these properties is thermal transport, thermal conductivity of materials. That involves many different calculations that you have to combine together. And that was only possible recently with the advent of these new technologies, these new machines. Okay, so within this approach, density functional theory is the theory of choice. Is what mostly everybody uses in this field. It's very widespread, and it's having an impact on science, which is huge. Not only materials modeling, but in quantum chemistry, in drug design, and actually the developer, the inventor of density functional theory, which was Walter Kohn, got his Nobel Prize in chemistry because it did really help quantum chemistry to become a technology which would be predictive and fast enough for very complex molecules. So the use of density functional theory has really exploded in the last 20 years. So this is something that I took from this paper of 2012, but then I looked at in Web of Science of the evolution of how many times the papers of density functional theory so density functional theory is used in publications, and you see that the growth is really quite exponential. I stopped in 2021, but this is growing still. So the number of papers published using DFT is really huge. And it's not only increasing with time, but the percentage of papers in these fields, in material science and in chemistry, that are using DFT is also growing. So it's not only the absolute number, but the percentage of papers that use DFT. So for instance, I show here the number of papers, or the number of papers mentioned in DFT compared to the total number of papers published in these three journals. This is a purely chemistry journal, but this one here in yellow is material science, is interfaces in materials. So you see that from 10 to 20% of the papers are now using DFT. So it's really become a very, very widely used technique. I would say that in physics or in chemistry is the most widely used technique, even compared to experimental techniques. So let me switch now to SIESTA. So SIESTA is the code that we have developed in this area. SIESTA is a density functional theory code, like many other ones, but from the beginning it was aimed at efficiency. So it was aimed at doing things in a slightly more approximate way, but to minimize the time to solution. So to make calculations much faster than the usual density functional theory codes. Now, SIESTA was done with that idea, but also with the possibility of cranking down the accuracy of the simulation as much as you would like. So it's a code that allows you to do very quick calculations, but also calculations which are very accurate and always in a time which is less and less expensive than other standard density functional theory codes like plane waves. And that from the beginning was independent of the computational platform. So it was an idea of how to do things that did not depend that you would have a large supercomputer. And actually, SIESTA was developed initially in the 90s, where we didn't have this high performance computer with so many nodes like we have now. SIESTA was a pioneer in what is called linear scaling, DFT, which means DFT calculations that only scale linearly with the number of the atoms in the simulation cell. And that was at the time a very, very remarkable achievement. Since then, several codes have provided similar linear scaling capabilities, but SIESTA was really the first one to scale linearly, allowing us to go to much bigger system than other codes. So what is SIESTA doing? What's the basic idea of SIESTA? So in DFT, you have two steps, let's say. The first step is to discretize your differential equation for the electrons, and you do that using a basis set. So you expand your wave functions in terms of a given fixed basis set of basis functions with some coefficients. So you transform this continuous problem into a discrete problem, a problem on a small or a finite number of coefficients here. And that's always done in density functional theory, but the way you choose this basis set determines the algorithms and the theory that you have to use to solve your problem. In solid state physics, in material science, typically people use plane waves because they describe crystals. So plane waves are very good for that. But in chemistry, chemists use mostly Gaussians, not because they are especially good, especially accurate, but because they are simple to compute. The computations you have to do with Gaussians are mostly analytic, so that's why they chose them. In SIESTA, we choose something which is more similar to Gaussians than to plane waves. It's also orbitals which are centered on the atoms. It's atomic orbitals, but they don't have a functional form like Gaussians. They are numerical orbitals, and they have a compact support. So they are zero beyond some given radius from the nucleus of the atom. Okay. Now this kind of atomic orbitals is very efficient because we have very few of them. You can very accurately describe molecular orbitals or solid state wave functions. And you can see that very easily, for instance, in the hydrogen molecule, just with two orbitals, which is the one s orbital of each hydrogen atom, you can describe quite accurately the bonding and the anti-bonding orbitals of the molecule of hydrogen. Now, just using one orbital per atom is very extreme. You only get a qualitative description of the molecular orbitals, but using a few atomic orbitals per atom, then you can have a very, very accurate solution with many less atoms than in plane waves. So typically, you would use 10 to 20 orbitals per atom in a realistic system, a problem with a very good accuracy, whereas with plane waves, you would need hundreds of plane waves per atom in your system. Okay. So in SIESTA, that's the kind of basis set we use. It's a product of a radial function and an angular harmonic and a spherical harmonic that provides the angular dependence. This radial function is the one which is confined. It is zero beyond some cutoff range. And that's what gives SIESTA the competitive edge. These are not analytic functions, but they are compact functions that give you very sparse matrices. Okay, so now that when you have chosen the basis set and made this expansion of the wave functions in the basis set, then you have to solve your Schrödinger equation. And to do that, when you discretize, you transform the Schrödinger equation into a eigenvalue equation. In particular, this is a generalized eigenvalue problem. You have a matrix that you have to diagonalize, but then the basis orbitals have overlap. They overlap with each other. So you have to solve this generalized eigenvalue equation with an orbital overlap here. And these matrix elements are just the matrix elements of the Hamiltonian in your basis functions. Okay, so these are just numbers which are integral that you can compute. The advantage of SIESTA is that both computing this matrix of orbitals, since they have compact support, these matrices are very sparse. If you have a very large system, only a few atoms, a few orbitals overlap with a given orbital which is very close to them. So there are many, many zeros here, and you only have to compute a number of orbitals which grows of overlaps that grows linearly with the size of the system. And once that you have this very sparse matrix, you have to solve it. If you solve it with brute force, just diagonalizing your matrix, that would be an order n cube operation. But you can also use the sparsity of this matrix, and you can use also some approximations to make this scaling go down even to linear scaling, to order n. And that's what SIESTA does. SIESTA computes these matrices in order n operations, and then it can solve this matrix with a variety of solvers going from n to the cube, very accurate, essentially exact, to order n, which has some approximations and errors too. Okay, so these basis functions are really, really accurate. So this is a comparison of SIESTA with some plane waves code, which is a BASP in the study of impurities in graphene, for instance, some metallic impurities. And you see that properties like bond lengths, bond angles, energies of the impurity, they really are very accurate compared to BASP, which is the state of the art in this material science field. Another example more in the quantum chemistry field, this is a set of segments of DNA, so base pairs which are bonded by hydrogen bonds. This is like 30 of them, and this is showing the accuracy of SIESTA, the results of SIESTA for the binding energy of these base pairs compared to a much more accurate quantum chemistry method, which is called MP2. And you see that the errors are really very small, are about 1 or 2 kilocalories per mole, which is what people typically call chemical accuracy, with a much less computational effort. So these basis sets are very accurate, even if they give you a much faster solution than the typical Gaussian or plane waves. Okay, so this is actually what SIESTA is. As I was saying in the beginning, SIESTA was developed in the 90s. And actually in the 90s, we could solve in a single CPU workstation of the time, in 95, a system with 800 atoms, which was a whole turn of a DNA chain. That was never done before. And actually with plane wave codes, currently this would already still be a quite expensive problem. So now if you have much larger computers, then you can do much larger systems. Of course, this is an example of a publication a few years ago where they were looking at a device. This is a material where you have two leads where you put a different voltage, and these are two tips of the STM apparatus that you can look at the surface and see how the atoms interact and how the currents are going. This calculation would have several tens of thousands of atoms. Okay, so this is why SIESTA is really very much used by the community. It allows cheap calculations in small computers, but it also allows you to do much bigger systems in large computers. And the papers that have description of the code and the method have already reached about 15,000 citations. So it's really very much used by the community. It has all the characteristics and the utilities that every density functional code does, like doing molecular dynamics, analysis tools, and so on. But it also has some specific features which are very specific of SIESTA. So for instance, one is this trans-SIESTA capability, which allows you to study electronic transport and electrochemistry with systems which are out of equilibrium and connected to electrodes. And I will show an example later. It also allows you to do calculations which are not static, in which the electrons are not in the ground state, but are moving, are evolving with time. And that's done with what is called time-dependent density functional theory. And we also have a package in SIESTA that allows you to split your system in a part which you describe with quantum mechanics, like usually in DFT, but also another part in which you describe it with classical force fields with molecular potentials that allow you to do much bigger systems, because the expensive part will only be the quantum mechanical part. That's also quite unique of SIESTA. Okay, so in developing SIESTA for high performance computing, and this is something that is not strictly something from SIESTA, but an approach that we took in all the codes in MaX, was to evolve from an old vision and the structure of the electronic structure density functional theory codes in our community, which has a monolithic structure where most of the code was a monolithic structure that involved everything from the electronic structure solution to the molecular dynamics to the numerical libraries. It only used very small standard numerical libraries like Scala-Pack or MPI, but everything else was in a monolithic version of the code. We moved that into a much more modular kind of separation of concerns concept, in which the density functional theory driver, the main engine, is a very small part of the code, and we separate all the numerical intensive parts into libraries. So many of the things now are put into libraries, numerical libraries, which we try them to be as more general purpose as possible, so that we can share with other codes and we don't have to invent the same algorithm once and again. And that's the largest part of the codes right now. So the density functional theory idiosyncrasy of each code is restricted to this very much smaller part of the code. And then we also have other higher level structures that deal, for instance, with the nuclear dynamics, or even workflows in which you can link properties which are computed by several runs of the same code at a higher level. Okay, so for instance, this thermal conductivity property that I was explaining, that can be actually done in this way because it involves many different calculations of different structures and different properties. And that splitting of the code has been really instrumental. We are using it. It allows you to use actually developments of other people and other groups. So I'm mentioning here two initiatives. One in the US, which is ELSI, which is an initiative to develop essentially eigenvalue solvers, which are very efficient, and they are available for linking many codes. And there's a bunch of codes in density functional theory which are already using the libraries that they are providing. And the other one is the electronic structure library. That's an European initiative promoted by CICAM, in which there is also part of eigenvalue solution, but there are many other libraries which are devoted to different things, like exchange correlation potentials, or Banner functions, or libraries for input-output. There are many things that now are encapsulated in libraries, and that different group codes can just use and link. So you have here a number of codes that are using these libraries: the GPO, Big DFT, which is another MaX code, Quantum Espresso, another MaX code, and so on. And SIESTA is one of them, providing input to these libraries. So that has allowed us really to develop SIESTA as a much smaller core of the code, and using all these developments that can be used by many other people, and we can also take in profit of the developments of other people in this area. So, for instance, besides these libraries for basic functionalities like exchange correlation, pseudo potentials, and so on, we have these scripting tools in which you can access data structures inside the code. You have access to other Poisson solvers, for instance, with different boundary conditions than the ones that we had in SIESTA. Again, you have different solvers for the eigenvalue problem, etc. So this is a very interconnectable structure in which you can take profit of what other people do. So let me go to the main time-consuming part of SIESTA, which is the solver, is the eigenvalue solver. In SIESTA, if you have relatively large systems, the solver typically takes about 90 to 95% of the CPU time. So this is the time-consuming part and the bottleneck of SIESTA in terms of computing power. So in SIESTA, the straightforward thing to do is to use direct solvers. And you need direct solvers. You cannot use iterative solvers because you need most of the states in your density, in your Hamiltonian. In plane waves, you only need a few eigenstates, so you can use iterative solvers. But in SIESTA, we need most of them, so it really pays to do a direct diagonalization. And with that in SIESTA, you can use straight scale-up, which is what we were doing many years ago. But now we are moving to these alternative packages like ELPA, which is very much optimized, and that it's giving an edge of performance in SIESTA. These solvers are always cubic scaling, so this ordering scaling that I mentioned before is lost if you use this kind of solvers. But again, we can use all the work that other people are doing. So in this LC initiative, they are developing many different solvers in the same spirit, ELPA, but also other solvers like PEXI that I will talk about later, and many others that we can directly take profit from. And Alberto Garcia is the person linking SIESTA to this electronic structure library in collaboration with Victor Yu at Duke University. So that, for instance, allows you directly to take profit of the GPU acceleration of LC. So in LC, there is already the possibility of using GPUs, and just using out of the shelf the ELPA library, we can just put SIESTA in GPUs. And since this is the most time-consuming part of the problem, then we can take profit of the GPUs in our system. So you can get a speed up of a factor of 4 or 5 just in using a single node. If you go to 2 nodes, then it's even better. So again, this is only because we are using libraries which are standard and let's say developed by large groups of people. So here in this graph, I show you some strong scaling data. So this is a calculation in a very large system. So it's a part of a protein of the COVID virus which is solvated in water. So it has really a large number of atoms. It's more than 8,000. And I'm showing you here several things. So this purple line here is the scaling of the diagonalization with the number of nodes. It scales nicely, but then it saturates at a relatively low number of nodes. But you can use GPUs, as I showed you before, and you can have a nice speed up just using the GPUs out of the shelf with LC and ELPA. But then you can use other solvers. These are just a straight diagonalization, but you can use other solvers like PEXI. PEXI does not compute the eigenvalues or the eigenvectors. It essentially solves the density of the system, and it does it so by inverting matrices. So it inverts this H minus S matrix, and from that it computes the density matrix. And PEXI has 2 main advantages. One is that it is extremely scalable in terms of number of processors. So you see that you can reach much bigger number of processors while maintaining a quite good efficiency. And the second thing is that the scaling of PEXI in terms of the number of atoms in your problem is not cubic, but it's quadratic at worst. And that's because PEXI uses very well the sparsity of the Hamiltonian. So in making this inversion, it doesn't compute all the elements of the inverse. It only computes the elements that you need. And that gives you a very much speed up. So PEXI is really good because it's scaled with many nodes, but also because of the scaling with the number of atoms is very favorable. So I'm showing you here in this very complicated slide. These are 2 different systems. This is a DNA strand with 17,000 atoms. These are these curves here in blue and green. And I'm showing you also another system, which is a 2-dimensional system. It's a stacking of a graphene plane with a boron nitride plane in a wire pattern. So the 2 lattices have slightly different angles. So they form this very large periodicity moire pattern in which you need 12,000 atoms or more than 12,000 atoms to simulate. And those are the curves which are here in the middle, this 2D system. Okay, so these two sets of lines are the results with PEXI, and you see that they scale very well with the number of orbitals, but also that if you have a system with small dimensionality like this one-dimensional DNA strand, it's much faster than this two-dimensional system, which is this graphene stack. And both of them are faster and scale better than the straight diagonalization. So diagonalization, it wouldn't care too much about the dimensionality of the system. It would scale well initially, but up to a limited number of nodes, and then it will saturate, which you don't see in PEXI. So PEXI is really the way to go in these very large scale problems. Okay, so just to finish in the last 5 minutes, I will tell you something about SIESTA, which, as I said, is one of the main characteristics, the main distinctive points of SIESTA compared with other density functional theory codes. SIESTA just solves the same equations of DFT as any other code, but in a situation which is quite uncommon, which is a system which is connected to two electrodes, which are actually semi-infinite. These two electrodes extend to the infinite in the right and the left. And in a case where you put a different voltage between the two electrodes, okay? So you have an electric field in between, you may have currents, and this is a system which is out of equilibrium. You have currents and you have a voltage between the electrodes. And that's relevant for at least for two specific problems. One is electron transport in devices. If you have here between the electrodes, you have a molecule or you have a transistor or something like that, a nanoscale device, then you are interested in looking at currents there, and that's the situation you will find. And the other problem is electrochemistry. It's the same problem, but here you have an electrolyte, and you would look at chemical reactions and the interface between the electrolyte and the electrode. But formally, the two problems are similar, and SIESTA can solve these kind of problems. And this was actually one of the calculations I showed you before. That was a SIESTA calculation of the currents going through this device when you put a difference in voltage between the left and the right electrode. And you can also address how much current is going through these leads that are connected with STM tips to your surface. Okay, so in SIESTA we can do that, and that's quite efficient, but we are currently taking profit of another development that we have in SIESTA, which is, as I mentioned before, to mix quantum mechanical calculations with empirical classical potentials for part of the system. And in this electrochemistry business, so if you have a large electrolyte here, many of the chemical reactions that happen, which are the ones that need the quantum mechanical description, are happening at the interface with the electrode, but not in the bulk of the electrolyte. So you can actually quite accurately describe the electrolyte with molecular potentials, with molecular atom modeling, and make much bigger calculations. And that's what we are doing here. We are seeing what is the scaling of this huge system going from 1 unit of water with 236 atoms, which is this box here, repeating that many times from n equal to 1, from 1 to n to 10. So going from 236 to 2,360 molecules of water in this electrolyte system. Those are calculations done in Mare Nostrum, but using a very small number of cores. So we were using just 384 cores, not processors, but cores, in 96 MPI processes. So this is quite a small scale calculation. And what I'm showing you here is the scaling as a function of number of units, these 236 units that I was showing you before. And I'm showing you three graphs. One is the diagonalization, the straight diagonalization with the usual solvers, scale-up or ELPA, and that scales quite badly with the number of units, and the CPU time is really quite long. So in these 300 processors, the largest system would take 10 to the 4 seconds. So that's really is not admissible to do long dynamics. Now, if you do SIESTA, which is based on something similar to PEXI, then the scaling is much better with the number of units, but still it's a quite costly calculation. But if you go to this mixed quantum mechanics, molecular mechanics scheme, then the scaling is even better. It's still linear, but much more flat, and you only take a few seconds per empty step. So with these calculations, you can actually afford to make 1 picosecond of simulation per day in this very small partition of the system. So if you scale it up to many more codes, then you can have really realistic calculations with realistic times in a quite reasonable CPU time. And that's what we're doing. We're trying to parallelize TransSiesta. TransSiesta is not using these libraries of solvers that I was saying before. It's much more handmade, let's say. The old parallelization of SIESTA, it didn't have a parallel inversion. It was just using a parallelization over MPI processes over the energy points. So remember in this PEXI that I mentioned before, you have inversions, and you have to do that for a number of points in your sampling here. So P is the number of points here, and that's where you can trivially parallelize. So that's what we did here. But then every inversion was done with LAPACK, and the only parallelization there was on OpenMP. Now we have extended that to do this inversion also with MPI processes with the ScaleAPACK, and then we go from this nice scaling for very small number of nodes that saturates very quickly to a situation in which we can use relatively efficiently like 50 processes per energy point. So that puts TransSiesta into using about 5,000 processors, which already is becoming to be quite interesting. So you can tackle these kind of problems with a much bigger part of the machine. So just let me finish with a few words about deployment. Daniel explained that a bit earlier. In SIESTA, we have refined and made a much robust building scheme for SIESTA, which is based on CMake. It allows the deployment in many different machines and in new platforms. And it also allows to automatically download the core dependencies of SIESTA quite automatically. And it also allows to deploy the GPU support with existing LPA installation automatically because it will detect it when you deploy the code in the machine. So it also allows you to provide the following options of installation in any of the EuroHPC centers. So it's able to use the SPAC recipes or the easy build recipes. So it's really becoming quite automatic and efficient. We can also provide codes, binaries with the Conda for general usage. So SIESTA, as Daniele was saying, has been developed and compiled in all the non-ARM EuroHPC machines, including GPU support. The GPU, the new Intel and Cray compilers are supported out of the box, and we are currently working with the ARM support that will be expected to finish in 2025. And this is again the same graph that Daniele was showing, a bit less pretty than his. So in SIESTA, we have deployed it in all the main EuroHPC machines in Europe. We are still working in some of them, essentially the ones that have ARM, but in the other ones we have demonstrated, and many of them benchmarks and actual modules in these machines. And with this, I will finish. Just a few links to tell you where we can be found. So the main place would be the SIESTA webpage. You can get directed from there to any other of the relevant sites. So the Discord server, the online documentation, the developers page, and so on. And with that, I will finish, and we'll be happy to take any questions you may have. Thank you.
So thank you a lot, Pablo, and also Daniele, for your very nice presentation, a very illuminating talk. I think you have already answered likely lots of questions that people could have. So if you have questions, please enter them in the question module.